Okay, so till now we have talked about order notation and how you can look at codes and think about their order notation. But there is one particular instance that we have not seen in examples. So we have seen examples where you have some sort of for inside for and loops, and by for I mean to say loops inside loop, or there is some part of code and then there is a sequential part of code that goes after that. So we understood that if they are particularly independent, we say you can use some sort of multiplication in this. So these two are related by multiplication, and when they are executed sequentially, you have a addition relation, right? These are two relations that we talked about. But one particular instance that we have not seen is something like this. Say you have a recursive solution. You have a code that implements a recursive function. Let's say you have a simple function Fibonacci of n. So Fibonacci of n means what is the nth Fibonacci number, okay? So finding nth Fibonacci number is a problem in itself, and we know that there is a simple recurrence that you can simply return if n equal to say 0 or n equal to 1. In that case, let's remove return from over here. You return 1, or else you return Fibonacci of n minus 1 plus Fibonacci of n minus 2, right? That's the recurrence that we have for Fibonacci, right? Now with these relations in place, how do you think you will calculate the time needed for calculating the Fibonacci number, right? So whatever we talked about earlier won't be able to solve the recursive kind of variation directly using that, right? So in a crude sense, we really need to find the number of executions that are being done in these code. But again, since it's recursive, we have to keep track of a lot of things, right? So when it comes to base case, it takes just order 1, but what does this takes? Like, this is really weird, right? Similarly, other function like merge sort that you might have read about, that you have an array, you want to sort this, okay? So you divide this array into two parts, take these two parts individually, then recursively solve them and get the sorted array, and then finally merge them to get the final sorted array, okay? So this is the merge sort routine. And so you first divide, you sort individually by using recursive solution, and then merge them, okay? So this is the merge sort solution. So again, this also follows some sort of recurrence. How do you find the time complexity of merge sort? Okay, so to help you with all of these calculations, there is a nice theorem that you can use directly to calculate time when you have time complexity when you have recursive problems. So we will be discussing that in this. So there is a theorem called Master Theorem. Sounds cool, isn't it? Seems like it will solve everything. And it does solve a lot of variations of recursive solution. So Master Theorem is a theorem that helps you get the time complexity when the recurrence for time complexity, like the T of n, basically means how much time will it take for an instance of size n to solve, okay, is equal to the recurrence for this is of the form a times T of n by b plus c, okay. If it is of something of this form, then you can use Master Theorem to solve the recurrence and get the actual complexity, okay. So in case of merge sort, what we see is that just if you know about the merge sort algorithm, what it does is that they divide it into two parts. So that division is hypothetical, so we don't do any operation, right? So we just do t of n by 2. That's like recursively solving this. So let's say t of n is for the whole array, right? So t of n by 2 is the time taken by the half of the array. That's the recursive idea. T of n by 2 for this, and then you merge them using order n, right? There is a merge routine in merge sort which takes order n. So for merge sort, the recurrence would be something like t of n equal to, there are two separate instances that you call, so 2 times t of n by 2 plus order n, right? This is the time complexity that you need to solve, and this is exactly of the form this, right? So we will be able to solve merge sort using that. But again, if you see Fibonacci number, it becomes pretty difficult, because for this it is not exactly of this form, right? That there is n by 2 and n by 2. Every part that it dissolves into is not of same size, so we cannot really do a Master theorem on this. So this Master theorem is applicable in a lot of recursive solution, but not all. So in most of the solutions which have equal size of partition in all the recurrence will be solved by Master theorem. So now let's quickly look into the Master theorem. So we would not be going into the exact theorem statements, but I would be giving you the exact technique that you would need to calculate the answer or the time complexity for any theorem, any solution idea that follows this recurrence, okay, using Master theorem. Okay. So you are given something like this, okay. So let's take down steps. Step 1, okay. What's the step 1? Calculate. So not calculate, you can say note down A, B, C, or you can think they are small and capital all same, okay. So this A is same as this A, okay. This is this A, B, C. We are transforming this variable. So this might not be exactly some number directly, so there can be some other things as well, but we just take the numbers for now. So let's take these three into a variable ABC, okay. So this is a theorem, so we would be able to formulate a step-by-step algorithm or process to find out the time complexity, okay. So then you calculate log base B A, okay, and write n to the power this at a place and C, okay. Calculate these two pairs, like this is obviously there, this is already present to you, like in this case the C is order n, okay, B is 2 and A is 2, okay. So this is order n and you need to calculate this part, okay. So if you see in this example, B is equal to 2, A is equal to 2, C is equal to order n. So over here you will see this is n to the power log 2 2 comma order n, right? This is what you have. Uh, let's keep this in order as well. Okay. So even if we don't write order, things right here, since we are suppressing coefficients everywhere, it generally means order, okay. So we have order n, okay. Now in this order, so if you just simply reduce this, you get order. So 2 base 2 is 1, right? So order n comma order n, right? Nice. So now once we get to this, once we get to the step 2, now there is this final step, which is a case analysis. If order of n log b a and order of c, or in fact c is already in order notation, is same, okay, is same, then answer is c log n, okay. If order n log BA is greater than C, then answer is order n log BA. Else the answer is order C, or C, not order C, since we know that C is already in order notation, so it's order C. So this is the exact technique. So this part over here, this is what you will need to remember. Just remember this term over here, n to the power log BA, right? This you need to calculate. So let's quickly do just quickly run this on the merge sort that we were running over here. So both of them are same, right? So the answer is C log n. So C is order n multiplied by log n is order n log n, right? Right? N times log n order is order n log n. So this is the time complexity of merge sort. Okay. So let's quickly look at some examples that should help us, so that these things stick with you on your mind, so that you don't forget them even if you want to. Okay. So let's take an example. Let's say T of n is equal to 27 times T of n by 3 plus n to the power 3. So rather than writing it n to the power 3, we write it like so. So this is the recursive step, and the other part, the non-recursive part, takes you order say n cube, okay, something like this. So how do you find the time complexity for this? Okay. Now, if you quickly apply Master Theorem on this, you will notice that, let's go step by step. A is equal to 27, B is equal to 3, C is equal to order n cube, okay, and then n to the power log base 327 is equal to n to the power 3, right? Right, this is as well n to the power 3. So now this and this are same. So when we have same, you know, you just add a log n to the thing. So the answer for this would be order n cube log n. Okay. Let's take one more example. T of n equal to 2 times T of n by 2 plus n squared. So simply applying Master Theorem again, A is equal to 2, B is equal to 2, C is equal to order n square, right? Okay. So next you just calculate n to the power log 2 base 2, that is equal to order n, that is equal to, sorry, not order n, that's n, and then we compare these two orders, right? Like these two orders. So now n square is more, right? So if this is more, then this goes, this is your answer. Okay. The same example with some difference. T of n equal to 2 times T of n by 2 plus order 1. So in that case, what you need to do is just simply again note down A equal to 2, B equal to 2, C equal to order 1, and you will get, from this side this will repeat, so you get order n, and this is order 1, so your answer is order n, right? So the answer is order n. This is your final answer. So just calculate these two numbers, n to the power log base ba and the c, compare them. If one of them is more, just report that, or else you just if they are exactly the same, you just multiply your log n. Now why is this working? That really depends upon the recursion tree, and you will need to look at the formal proof of that, formal proof of Master Theorem. But again, that's not really required at a lot of places, so we will be skipping on that. If you want to read, you can go out and Google that, and or even you can read on CLRS book. So that's there. Now let's look at one more problem, which is pretty interesting. Let's say you have something like this: t of n is equal to 8 times t of n by 2 plus n cube by log n, something like this. Now how do you apply Master Theorem to this? So again, if you do this, a equal to 8, b equal to 2, c equal to order n cube by log n, right? If you start doing this, and if you do 8 base 2 log, so that would be n to the power 3, right? And this is the first parts, like n to the power this, and this is the second parts. Now if you compare them, it might seem that this is larger, right? And you can report order n cube. But the thing is, the recursive idea of Master Theorem doesn't work on these logarithmic terms. So whenever you have a logarithmic term, just ignore that. Okay. So either you can say that Master Theorem doesn't apply, so we cannot calculate, or if you really have to calculate, just do this, that you just ignore this log n part for some time and see that n cube and n cube are same, so you just report order n cube log n. Okay, so this is not perfectly correct, but at least this is order notation, right? So we know that order notation is a upper bound, so this will work. Okay, so for logarithm being present in the c part, ignore those when calculating using Master Theorem. But in its true sense, Master Theorem doesn't apply when you don't have a non-polynomial expression over here. Okay, so that's all on Master Theorem. So if we quickly revise on the brief idea of Master Theorem, like the steps that you need to follow: find out the recurrence in this form, write down ABC, okay, in the three variables, calculate these two values like n to the power log base ba and c, and check whether they are same. If they are same, you have a new login being added to it, if they are not, then you have n log ba greater than c, or else like it's just c, because if whichever is greater, you will report that as the answer. That's it. Okay. Uh, so that's all on Master Theorem. See you in the next video.